Okay, today we're going to actually calculate volume, which is actually kind of a tricky thing if you think about it, because most shapes, I would find the volume of this classroom. Don't I have 3 different dimensions I have to deal with? You know, think of an X, a Y, and a Z. Well, in Calc 1 and Calc 2, we can only deal with one independent variable.
Minor.
Oh, so we're very specific on what we can do. So if you go back and look, like in our related rates problems, right? We had circles, we had squares, we had cubes, we had spheres, and that was pretty much the only shapes we dealt with, wasn't it? Because those are the only shapes that have one variable to describe them. Even something as simple as a rectangle, I need 2 variables. So we tended to stay with really simple shapes that had one variable. So what we're going to do today is kind of an interesting concept. Okay? I'm going to take just a simple region in the XY plane. Okay? And I'm going to rotate it about the x-axis. Whoa. Now, this will create something kind of interesting. So it's kind of like this, right? I don't know if I can do this very well. When I was in 7th grade, I took a woodworking class, and my older brother did the same class earlier, and he became addicted to it. How many have ever used or seen a lathe? You know what a lathe is? That's why I learned to use one. My brother used to make things. A lathe, you have something here, maybe think of it almost like the thing, when you eat corn on the cob. You guys ever use the little prongs? I always think that's cheating, you know. But kind of like prongs, and you put a block of wood in there. And then what the lathe does is it spins really fast. So you take a blunt object like a metal bar and you chip away at this thing. And so my brother would make things like, you know, candle holders, you know. But he actually used to make mugs, and he'd hollow them out. But what you have is the perfection of the circular motion. When you're all done, this thing looks circular in nature. All of its cross sections are perfect circles. So what we're essentially doing here is the same idea. Like a lathe, this thing is perfect when I rotate it. But it's not a sphere. No, it's not. It's not even like a sphere. But if I took this thing and I sliced it right here, and then I set it down, that's not a great picture. What does it look like? I'll give you a hint. They play it on ice, and they have long sticks, and they whack it around, and they try to score with it.
Puck.
It's a hockey puck. It is literally the exact shape of a hockey puck. The mathematical term people use is a disc. It's basically a hockey puck. Can I find the volume of that hockey puck easily enough? Well, what is another name for that? How about if I drew it this way?
Radiant.
Like a can. What would we call this thing?
Cylinder.
Well, you're 1% right. Circular. So yeah, the word cylinder doesn't, by the way, just so you know, in Calc 3 you do this all the time. The word cylinder does not in any way imply circular. There's an infinite, just like if I said polygon. There's no, I'd have to tell you what it was. If I said prism, I'd have to tell you what. So cylinder just means it's 3-dimensional. Circular cylinder is the can. And we know what the volume of this can is, right? It's the area of the base times the height. We know that. That's universal. A circular cylinder is a very easy thing to work with. Is this a circular cylinder? Yeah, but the height is the thickness. I can see the circle. That's easy enough. What is the radius of this thing? Wouldn't this be the radius? So let's call that yi, and let's call that delta xi. I'm going to do a slice, and I'm going to pull out this hockey puck, this disc. So I need to describe the ith volume. Because why? Well, there's a whole bunch of them. So it should be pi r squared height. Well, my r in this case is the y, and my height is the thickness because it's on its side. Now, what you're going to find over the next few classes, where we're doing a lot of things with different types of volumes. We're going to do three different lectures or three different topics where we're calculating volumes, and they're all different. But in most every case, whatever the thickness is and whatever I'm using here are usually going to be opposite variables. So if I had a delta y, then the other term's probably got an x. It's always going to work that way. So what I'm going to do is swap out y for f of x here. But I could also do this sideways, understand? So then we do a different switch. We're going to do a whole lot of problems. So this is called volume by slicing. And very specifically, this is called the disk method. Okay? Because that's the shape of the thing I'm going to get. Now, I could also do a rotation around the y-axis. We will do both, just to see what it looks like. So consider the following. The region bounded by y equals, let's say, x squared, y equals 0, x equals, I don't know, 3, is rotated about the x-axis. Find the volume of the resulting solid. This is the language we typically use. So when I say solid, I mean it is going to be a three-dimensional shape when I'm all done.
Do you mean y equals y squared or y equals x squared?
So what did I write? Oh, thank you, Jay. Y equals x squared. There we go. Y equals x squared, y equals 0, x equals 3. So what does this look like? It is always a very good idea to draw the picture, okay? Don't try to set this up in your head because you could make a mistake. So I've got y equals x squared, x equals 3, y equals 0, and I'm going to take this and rotate it. So what is that going to look like?
Cone?
Not exactly because of the curve. You know, if you're in the military, you might have been woken up to this every morning. I don't know. I think it kind of looks like a what?
Trumpet?
Yeah, horn, bugle, something like that, right? It's going out. Do I need to have a specific shape to relate it to? No, but it helps if I have an idea what it looks like. So it kind of looks like a bugle. Okay, so I want to find the volume of this thing. So I'm going to take an arbitrary slice anywhere in here. I'm going to describe the volume of that slice. And once I describe the volume of that slice, I know then that leads to a summation, to a limit, and eventually a definite integral. We just want to jump directly to the definite integral, but I need to describe the slice first. So the ith slice will be pi y squared delta x, but y equaled x squared. So this will be what? X squared squared, or
X to the fourth.
x to the fourth. Good. Now they're the same. Is there a range of values on x? Going from here to here.
0 to 3.
0 to 3. Good. That's just right there. I've described an arbitrary slice. The next thing is we take the sum of all these guys, then we take the limit of the sum, and then we write an integral. Let's just go straight to the integral. Because what's the integral going to look like? Like that. So now I can say the volume. This is one slice. The entire volume is the definite integral from 0 to 3 of pi x to the fourth dx. Pi is just a constant. If you want, you can pull that out of the integral. It isn't going to affect anything. Antiderivative?
1/5 x to the fifth.
So 1/5 x to the fifth. What do I do with the pi? Can I just say,
Yeah.
can I say that? Sure. Pi is a number. I'm going from 0 to 3. What's 3 to the fifth?
243.
243. Most textbooks would probably write it this way, 243 fifths pi, or you put the pi in the numerator. It doesn't make any difference. That's my answer. That's it. It's not that exciting, but that wasn't very hard, was it? But this represents a volume. Last day we did areas. Okay, I want to do almost the same problem. I want to take the region bounded by y equals x squared, This time, I want to go x equals 0. By the way, that point right there was the point 3 comma 9, is that right? X was 3, so y was 9. So I want to take this exact same portion of the curve. But this time I want to go y equals x squared, x equals 0, and y equals 9. So I want almost the same picture exactly. But now I want this. And guess what I want to do with this guy? I want to go this way. So we're going to do this one about the y-axis. So I do that so you can see clearly, okay, what is this thing going to look like?
Bowl.
Yeah, it's a bowl. It's a gumdrop. In my Calc 3, we usually refer to this as a calculate bloomin' onion. You know, it's, boom, it's like a gumdrop. It's actually called a paraboloid. It's actually the formal name for this. It's a circular paraboloid, which is really cool. So when I do my slices now, am I going to slice vertically?
No.
The rotation went this way. So where are my circles?
Horizontal.
Yeah, they're horizontal. Everyone sees that, I hope. Your circles now are horizontal. This is why you want to draw the picture. So when I do the slice, I'm going to slice it this way. So the second problem, we're rotating it about the y-axis. I'll write that up here. This is problem number 2. Now, I used the exact same curve. Here I rotated it about the x-axis. There I'm rotating it about the y. Should we expect the same numerical answer?
No.
Why not? Well, first of all, are they the same shape? This was more of a bugle, that was more of a bowl. I think the shapes are very different. Is it mathematically possible that they could end up being the same? Yeah, I mean, I could have picked just exactly the right stopping point. But in reality, they're very unlikely to be the same answer. So, when I set up this guy, I do the same thing. I draw my disk as well as I can do it. I come back here, you know, kind of that sort of thing. But really the key is, what is the radius of my disk? This time, the radius is what? It's the x. So I'll put it right here. And what's my thickness this time?
What?
It's the y. So this is what I said earlier. Those are usually going to be the opposites. Okay? The thickness and the variable that represents the radius have to be different variables every time. I mean, just look at the picture. Like, thickness is this way, radius is that way. In that picture, boy, I hope this isn't one of those classes where we have 20 different pieces. So what does the ith volume look like here? Again, it's pi r squared. So in that case, what is it? Pi
Xi squared.
xi squared delta yi. Now, here's the rule, by the way. On every problem that exists, here's the rule. That determines the variable you have to integrate with respect to. I have a function here that's describing my boundaries. Could I turn around and write x in terms of y if I really wanted to? Could I write x as the square root of y? Sure. I could always turn around and rewrite x and y in terms of each other. What I cannot do is change the delta x into something with a delta y. I can't mess with that thing. The delta x is not going to be touched. So the delta x determines that I have to integrate ultimately with respect to x. So I have to make this x-ish. Over there, the delta y says ultimately I have to integrate with respect to y, so I'll swap out the x. Okay, well my boundary was y equal x squared.
So it's x equals root y. Well, y. Yeah.
How about just
E squared.
y? If y equals x squared, I got an x squared right here. Ooh, I don't need to be clever, do I? Does everyone see that? I just replace x squared with y because y equal x squared is my boundary. What is the range of values for y? It's not 0 to 3.
-3 to 3, but it's
Y.
oh for y. You're 9. 0 to 9.
0 to
9.
9. So now when I do this integration, my volume is the integral from 0 to 9 of pi y dy. Really that simple? Yeah, it's really that simple. More often than not, the level of difficulty is just trivial. It's just not going to be a hard problem. So this will be 1/2 pi y squared. 9 squared is 81, so 81 halves pi. Are these answers the same? Are they close? Well, 81 halves is what, 40.5? What's 243 fifths? 48.6. So are they tremendously far apart? No, this one's a little bigger though, isn't it? I could select a stopping point. It would not have been, I'd have to do some reverse engineering, but I could figure out a stopping point where they produce the same volume. But then every other stopping point would be a different volume. So there's literally only one number that would produce the same. So in general, no, they're not the same. So the idea with a volume by rotation is actually a fairly simple thing. I don't have to recognize the shape that I've created. I just have to be able to describe the slice. That's pretty simple, isn't it? Huh, okay. Find the volume of the, sorry, I'm saying this backward. Let me start with the region, sorry. The region bounded by y equals the square root of r squared minus x squared and y equals 0 is rotated about the x-axis. Now the question is, find the volume of the resulting solid. That's the way I meant to say it. Solid. Oh, well, what does this look like? This is kind of tricky. Well, what does that look like? Is it a whole one? I'll give you a hint. If I square both sides of that, what will I get? Square both sides of that. Won't you get y squared equals r squared minus x squared? Which would be x squared plus y squared is, wait a minute, what's that? Circle of radius r centered
0.
the origin. I like that one. Now, is this the whole circle?
No, it's the top half.
It's the top half. But this is how I figured out it's the top half. How do I know it's the top half? Because if I had solved for y, I would have got a plus or minus. So the bottom half would be the negative of the root. So I'm taking the top half of the circle and I'm doing what? I'm rotating it about the x-axis. What am I creating?
Half this here.
I'm
Just a full
taking the
sphere.
top half of the circle and I'm rotating it about the x-axis.
A full sphere.
I'm creating a sphere. Does everybody see that? I always gotta do that. I just made a sphere. This is how you make a sphere in Calc 1. I took a semicircle, I rotated it about the x-axis, and I created an entire sphere. Can we use this method to figure out this volume? So if I take an arbitrary slice, I'm going vertical because I rotated this way, and that's the way my function is defined. It's a little easier. Then what does this slice look like? Well, again, it looks like a disk. Nothing has changed in that regard. I know, my disks are terrible. What's the radius of my disk? That's the radius. That's x or y?
Pi.
So my radius is the y, my thickness is the delta x. So the volume of the ith slice is pi yi squared delta xi. I like that. Because what does y squared equal? What does y squared equal? Yeah, so this presents a really easy substitution. I don't have any square roots, do I? Because it's y squared. So this is pi r squared minus xi squared. Now, I've got to figure out the range of values for x. Go back to my circle. I have a semicircle, but its radius r. So wouldn't this point here be r comma 0? And what would this point be?
Negative r comma 0.
Negative r comma 0. Therefore, the range of values for x is what?
Negative r to r. Which is symmetrical, so you can cut
Maybe hold that thought. Okay, everybody cool so far? Can you now tell me exactly what the volume is? Yes, integral from negative r to r of pi times r squared minus x squared dx. And Chase points out that the limits of integration are symmetrical. Is my integrand either odd or even?
Yeah.
R is a constant, R is the radius. Constants are of degree 0, that's even. X squared, so is that even?
Mm-hmm.
Yes.
What can I do to make it easier?
Make it 2 times the integrand from 0 to r.
Yeah, that makes it just a little bit easier. All right, well, that's quadratic, that's not hard to integrate. So my answer, if you want, pull out the 2 pi. Might make it easier. All right, what's the antiderivative of r squared? R is a constant.
R squared x.
R squared x, yeah. R is a constant. What's the antiderivative of negative x squared? 1/3 x cubed, and I'm going from 0 to r. All right, so that means my answer is going to be 2 pi times r squared times r minus 1/3. What's r cubed minus 1/3 r cubed? A whole minus 1/3 would be 2/3 r cubed. So my final answer is 2 pi times 2/3 r cubed, which would be 4/3. Wait a minute, I've heard this formula before. What is that the formula of?
Sphere.
Is that the volume of a sphere? But you already knew that, right? Everybody knows that in, elementary school, junior high school. You know the volume of a sphere. What's the problem? This is how you derive it. You can't get that answer any other way. It's not possible to get that conclusion without doing what we just did. Which kind of is an interesting problem. It's one of those bucket list things that I don't know that I'm ever going to find out the answer to. But I have some questions that I'd like to know the answer to. The ancient Greeks in the 4th century BC knew about pi. They knew this formula. Calculus was invented somewhere 17th, 18th century, more than 2,000 years later. And it wasn't even in the first 100 years that calculus had been invented that someone figured out how to do this. We absolutely knew this as fact, but we couldn't derive it or prove it for over 2,000 years. How did they know? How in the world did the ancient Greeks know this formula when it took over 2,000 years for human beings to have the ability to actually come up with this answer? I think the answer is easy. I think it's the same place that Velcro and the pyramids come from. Aliens, yeah. It's like, duh. I don't know, maybe we will find out someday. I just find that to be one of the most cool questions you could ask. How did they know? There is no trail of evidence that suggests that anybody had any idea how to do stuff like this before calculus. Because it's not possible. There is no hidden secret way, but they knew this. I just find that to be cool. They knew all these properties of circles and spheres 2,000 years before we could actually derive or prove any of it. So the volume of a sphere can only be done through calculus, and we just did it. There are other ways you're going to learn how to do this in higher levels of math. This is not the only way. This is just the first way because we did it by a rotation. Kind of cool though, huh? You found the volume of a sphere by rotating an object. It's crazy. Okay? Well, it turns out if it's circular in nature, it requires calculus to derive. There's no way around it. Now, when you guys were going through school, you learned properties of circles. You learned properties of spheres, like surface area and other things. And maybe even your teacher was able to demonstrate certain things to you, but you mostly took the formulas at face value because there was no problem with that. Accepting these formulas on faith is not evil. Remember at the very beginning of the class, when we first defined the derivative, I proved to you the derivative of x to the n as long as n was a positive integer. Then I proved it for negative integers. And then I said, I want you to accept on faith that it's true for all real numbers. Because a week later when we learned implicit differentiation, I then proved it for all rational numbers. But I couldn't prove it for all real numbers until we got to logarithms. Then it's actually trivial. But you had no problem accepting the derivative of x to a power was power x to the power minus 1 once I showed you it was true for integers. I said it is true for everything, but we can't show it yet. There's a whole lot of math that still works that way. Okay? Limits. It's very easy to prove using epsilon delta that the limit of a sum is the sum of the limits and the limit of a scalar multiple is the scalar multiple of the limits. That's actually trivial. I can do each one of them in under a couple minutes. But to prove the limit of a product is the product of the limits, you might be a first-year grad student before you see that one. It's true, but it's really complicated. So we don't have any problem accepting it, but a lot of times we can't actually show it based on what we know today. So we have to say, I know it's true, I'm going to see the proof later on. And we're okay with that for the most part, right? Tell me you're okay with that. Mm-hmm. You don't always need to see it now. Okay. All right, let me do another one that's fairly simple. All right, we'll do a line segment. And the line segment's going to be the line segment, how about, hold on a second. All right, I'm going to take the region bounded by this triangle right here. That line segment, that horizontal line, that vertical line, and I'm going to rotate this around or about the y-axis. What shape am I going to get? Specifically again, cone doesn't imply the shape. Circular. Yeah, we have a bad habit in calculus. We assume that everything applies to a circle when actually nothing does. My car burns oil like you would not believe, so I have to add oil all the time. So I have a little funnel. A funnel's in the shape of a cone. It's not circular, it's a cone. It's elliptical. They usually aren't circular. Yeah, when you say cone, it doesn't mean circular. When you say cylinder, it doesn't mean circular. That's just the most common one we deal with. If I said prism, people are thinking of this, unless you've had chemistry. Then you're not thinking rectangular, you're thinking what? It's the only three-dimensional shape you've ever dealt with in chemistry. There's only one. It's not rectangular, it's chemistry, refracting light, Roy-G. Biv, all this stuff. Triangular. The only prism you'll ever deal with in that situation, actually in any science class, is a triangular prism. So when people say prism, everyone thinks, oh, you mean rectangular. Really? The chemist isn't thinking rectangular, they're thinking triangular because that's the only one you'll ever use. No, you actually have to say what type it is. Prism, excuse me, just means a three-dimensional bound by polygon. It'd be like if I said polygon, are you thinking square? Because it isn't. Square is very specific of the infinitely many. So we actually need to say circular if it's circular. Because a cylinder, when you're going to deal with them in Calc 3. You're going to deal with them all the time. And the vast majority of cylindrical shapes you deal with won't be circular, but you will deal with circular cylinders also. You'll deal with cones, probably circular more often than not. but elliptical is probably just as common, you know, in fact, in real life. So this is a circular cone. I'm pretty sure I know the volume of this, but I can't tell you why I know that. Oh, it's because I was told it as a kid. Probably weren't shown this. So let's do this. Let's do this. I like this problem. So I'm going to take that slice. I'm doing it about the y-axis this time. So you notice I keep going back and forth between my axes. I do that on purpose. So here's my disk. My radius is what? It's the x. My thickness is the y. So the volume of my ith slice is pi xi squared delta y. Now, I got to figure out a way to connect the two together. I need the x to be in terms of y. Can I do that? How can I do that? If y equals h over r times x, then what's x?
R over H times what?
R over h times y. Beautiful. Do you agree with that? Now, h and r are just constants. By the way, what do they represent in that picture? Radius and height, obviously. I just chose them as random constants, but yeah. So this would be pi r squared over h squared y squared delta y. What is the range of values for the y?
0 to h.
So y is going from 0 to h, which also represents, therefore, my limits of integration, right? So I can say with certainty the volume is the integral from 0 to h of pi r squared over h squared. That is all one big constant, right? H and r are just constants. Y squared and y. Well, that's not too bad. So what does that give us? That gives us pi r squared over h squared times a third y cubed from 0 to h. A lot of r's and h's. What will that be? Pi r squared over h squared times a third times h cubed. Does anything cancel? Do I get some canceling here?
H's. H in the denominator.
So I'm gonna have one h left over? Excuse me. So I'm gonna put the 1/3 in front. Huh. I think I've seen that one before. Isn't that the volume of a circular cone? What was the volume of a circular cylinder again? Isn't it pi r squared h? This is a cone, it's 1/3 pi r squared h. That's actually kind of important. That's actually important. Those of you who remember geometry, if I said let's pretend there's no inlet, that this is a perfect rectangular prism. If I used the same floor, but I had everything come up to a point in the middle, what's that shape called? They buried, pharaohs in those things. Pyramid. Do we know the volume of a pyramid compared to the volume of the prism? Yeah, we do. It's exactly 1/3 the area of the base times the height. And that's not that hard to prove. That doesn't require calculus. The volume of a pyramid is 1/3 the area of the base times the height. What's the volume of a circular cone? Exactly the same thing. 1/3 the area of the base, which is circular, times the height. That's kind of cool, isn't it? So the thing with polygon sides and the thing with circulars really have the same formula. The circular cylinder is area of the base times the height. There's a pi r squared. The prism is area of the base times the height. But then the cone, the circular cone, is area of the base times the height times 1/3. And the same thing for the pyramid. That's true across the board in geometry. That's kind of comforting that I get the same thing. Okay? Any question on this so far? Is this stuff hard? Shouldn't be. If your regions have nasty boundaries, right? If your boundaries were really complicated things, you might not be able to finish the problem. Could you always at least express the integral? So we're going to do one of those. region bounded by y equals cos x from 0, I'm sorry, from, not 0, negative pi over 2 to pi over 2, and y equals 0 is rotated about the x-axis. We want to find the volume of the resulting solid. So I have that. I'm rotating it about the x-axis. Is that going to be an ellipse? I haven't rotated it yet. Is this going to be an ellipse? Well, an ellipse would have a vertical tangent right here, wouldn't it? That slope is -1 and that slope is +1. So no, it's actually going to be kind of a pointy. I think the formal name for this shape is, give you a hint, they usually taste like lemon. What are these called? Small
Limes?
candies?
Lemonade?
Yeah, lemon heads, lemon drops. You guys know what I'm talking about? Little lemony things. You suck on them. That's a lemon drop, lemon head, whatever. Okay, it's not an ellipse. Why? Because an ellipse has a very specific formula. This ain't that. So this is basically a lemon drop. Okay. Your kid at Callaway probably come in a little box with a whole bunch of them. They're really nasty, bad for your teeth, but they're sweet. So I want this thing here so I can easily set up the integral. What I'd like to know is if I can actually solve the problem completely, do the calculation. So when I do this, again, so this is going to be y this time, and that's going to be delta x this time. So the volume of my ith slice, erase some stuff here. So it's pi y squared delta xi, but in this case y is the cosine function. Well, that seems easy enough. And what is the range of values for x? Right there, negative pi over 2 to pi over 2. Life is good. So can we say with certainty the volume is negative pi over 2 to pi over 2 of pi times the square of the cosine function dx? And there's some bonuses in here.
Is it that limits you can have it?
I have symmetric limits. Not only is the cosine function an even function, but I'm squaring it. Anything squared is an even function, isn't it?
Mm-hmm.
So can I use that to my advantage? Absolutely. So we will use that. And so this is, I'll put the 2 pi on the outside for now. 0 to pi over 2 of cosine squared. Beautiful. You can leave it on the inside or the outside. It doesn't make any difference. So now all I got to do is integrate the cosine squared, which of course is cosine squared. Oh, do we know that one? No. Can we know that one? Yeah. Turns out this one's kind of important. It hasn't come up really yet. It will. It will come up a lot next semester. It will come up a lot in physics, and it is one you want to be able to do. But there's a trick first. You cannot integrate the cosine squared directly. You have to use a trig identity. And it's not the Pythagorean identity, because all that will do is give you a sine squared, which is the same problem. You can't integrate sine squared or cos squared, so what you have to do is use the double angle formula. So I'm going to remind you what that one is. Most people, when you ask them what are the most important trig formulas, like identities, most people think the Pythagorean identities. I differ. I think the double angle formula for cosine. Why? Because I think I use it 100 times more often than any other one. It's the only one that's used in every conceivable capacity, so I'll remind you what it is. If I said the cosine of 2 theta, we know that's cos squared theta minus sine squared theta. I'm just being real generic here. Okay? when you're solving problems and you're trying to answer questions, you don't want necessarily two different trig functions. You might want the same one. So if I wanted this all in terms of cosine, now I can use a Pythagorean identity. Sine squared does equal what? What does sine squared equal?
1 minus cos squared.
1 minus cos squared, which would make this 2 cos squared theta minus 1. What if I want everything in terms of sine squared? Well, then cos squared equals 1 minus sine squared. So this becomes 1 minus 2 sine squared. If you look on the cover of any trig, pre-calc, or calculus book, it will always have all three of these together. Because they're all the same formula, but it's sort of what do you need at that moment. Now, I have a sine squared or a cosine squared. I want to write it in terms of that guy. See this? So I want to isolate that guy. So if I put these two together, add 1 to both sides, take half of both sides, I will end up with the blue one that works. Okay. Cos squared theta, if I throw it over, is half of 1 plus cosine of 2 theta. I want to do the same thing for the sine squared of theta. So if I manipulate, throw things over, and multiply both sides, then the sine squared theta is 1/2 of 1 minus cos 2 theta. And these are two of the most important identities we ever use in calculus. I can work with sine squares and cosine squares. I just can't integrate them. So in order to integrate them, I have to use the double angle formula and change them because I can integrate these guys. Those aren't hard. You with me? So, by the way, some textbooks will say, these are the double angle formulas, and they give a different name for these two. You know what they call, typically they call these? Half angle formulas, which I kind of laugh because it's the exact same formula. It's not a different formula. Well, we call this one the double angle formula because I'm starting with 2 and I'm going half. Well, then why don't I call this one the half angle then? Aren't I doing the exact same thing? One is double the other or one's half the other, depending on how you look at it. Yeah, the same formula. So see this? I'm going to do that. And this problem will not be difficult. Now the nice thing is, see that 2 and that 1/2? Can I cancel them? Yeah, sure. All right, what is the antiderivative of 1 dx?
X.
X. The antiderivative of the cosine I know is the sine. It's plus.
Half.
I only have two choices here, don't I? It's either going to be a half or it's going to be a 2. If I differentiate, it's a 2, so integrating it has to be a
Half.
1/2. And the quick check is if I differentiate, boom, okay, good. I showed you that trick last day, remember? If your argument is a scalar multiple of x, then the antiderivative just has the reciprocal of that scalar in front. We did this problem last day, if you remember. Now, this is going from 0 to pi over 2. So I have pi times pi over 2 plus a half sine of pi minus 0. Because remember, when you're doing the doubling, the 0 is always going to be 0. That's 0 sine of 0. Okay, great. Sine of pi. Oh gosh.
0.
Sine of pi is
0.
This is getting easier all the time. What am I left with? Times. Well, if that's not a weird answer, I don't know what is, but that's the answer. Pi squared over 2. You don't see a lot of pi squares, do you? Not very often. But that's the answer. And we got the answer by using a trig identity that for this class, I would say is very obscure. Next semester, this will not be obscure. This will be something that you actually use. Let's say you use it often enough that you actually do remember it. Okay, nobody remembers things that they don't ever use. But those are identities that you learned a long time ago in a trig and or pre-calc class, but you haven't really had cause to use them. We haven't had a lot of cause in this class, but it does come up occasionally. The integration of sine squared and cos squared are not friendly, so you have to use double angle formula. That's it. Okay, questions so far? Okay, I think I'm going to stop right there because the second half we're doing something. Oh, we're already there? All right. We're now going to do part 2 of the same thing, but it's going to be a little bit different this time. Okay? What if factor. So I've got my y equals f of x just like before. But I'm not using the x-axis this time as a boundary, but I want to do the same thing. I still want to do this rotation. So what's that going to look like? Something, this-ish, if you will. What is that? What do you think that is? What do you think that is? Actually, you had it more accurate.
A weird donut.
Yeah, does anybody know what the actual term is?
Washer.
Well,
Washer is the slice.
a tarus, a donut. It's not flat, it's not anything, but it's basically got a hole in the middle. It's got a hole in the middle. So how the heck am I supposed to do this one? Well, we have looked at this one before. Could I do big disk minus little disk? In other words, could I do the big disk on the outside and then subtract the disk from the inside? Would that give me the same thing? Okay, I mean, they do that when you go to the donut store, right? You buy the donut, what happened to the middle? It's called a donut hole, right? So you actually can have that. So if I said remove the middle section, we'd have one great big problem here. And we now know it's probably of the form from a to b pi f of x squared dx. But the inside one, if I said what is this solid, we know that's probably this one. So therefore, if we put the two together, because we do want to do this as one integration, be the outer one squared minus the inner one squared. Now the advantage to doing it as one integral, when I do this, there's a high probability that when I put all this stuff together that I'm going to get some combining or canceling. So I'll actually have less terms than if I did them individually. This is absolutely correct, but this is the longest way you could possibly do the problem. You want to do this because this stuff here may condense tremendously. Now, what does this look like when I do my slice? I'll do my best here. That way, so it's, there we go.
A washer.
That's not too bad, right? This is referred to as a washer. Now, the disk method that we just learned, it's exactly the same method. The difference is the washer has a hole in the middle. So the disk method is just one of these guys. The washer method is the outer one minus the inner one, which is technically a big disk minus a little disk. We call it a washer, again, because it has a hole in the middle. Okay, you with me on that? It's not a different method from the standpoint of I approach the problem, I can do one or the other. No, when I do my rotation, is it one big solid or is there a hole in the middle? That's really the only question you have to ask. Okay? And if I look at it that way, so let's do a problem we started class with today. I did the region bounded by y equals x squared, y equals 0, x equals 3 is rotated. Now, how did we start the class? I rotated it about the x-axis. Okay? Everybody cool with that? Now I want to take that same thing. Yeah, it's rotated about the y-axis. I have the exact same region, but I'm doing a different rotation this time. So when we did this the first time, we rotated it this way and we got that kind of a bugle shape. Now I'm rotating it this way. Am I going to get a bowl Well, we got the solid bowl. What am I getting now?
An empty one?
Kind of getting the rim of the outside. So if you think about the way we did it the first time, you have your bowl and you filled it up with, Cheerios. We found that volume the first time. The second time, I have a big round circular cylinder and I'm going to hollow it out in the shape of a bowl, but I only want the outer part. Does that make sense? I don't want the inside of the bowl. I want the outer part. So I need to do this. If I cut it vertically, those aren't circular, are they?
Mm-mm.
If I cut it horizontally, then what do I see? I see exactly this. Okay, I see that washer. Now I need to figure out each radius, because how do I do this? Well, we said it's the outer radius squared minus the inner radius squared. In this picture, what's the outer radius?
3.
It's exactly 3. This is my delta yi. What's the inner radius?
X squared.
Just x.
Yeah.
The inner radius is my x. My outer radius in this picture is 3. My inner radius is x, and x is obviously changing.
Mm.
So if I want to find the ith volume here, I do it like this. The ith volume is pi times the outer radius squared minus the inner radius squared. Delta y. Now going back, this is real nice. Since y equals x squared, can I just swap this out? Yes. So 9 minus yi, delta yi, and the y values will range just like they did the first time or the second time. That point was 3, 9, unless we forget. What are the y values ranging from? 0 to 9. So I can say with certainty then, if I can find my eraser there, that the volume of this strange shape is pi times the integral from 0 to 9 of 9 minus y dy. Well, that's a pretty simple integral. Most of the time, the integrations themselves will be somewhat trivial. It's getting the integral is the whole thing, isn't it? So this will give us 9 times 9y minus a half y squared from 0 to 9. So that would be 81 halves y. So when we refer to what we're doing today, we actually give this one name. First of all, we're doing a rotation about an axis. That's the key. We're doing a rotation about an axis, and then we're slicing the circular part. My shape is either going to be a disc or it's going to be a washer. I don't choose. Everybody understand that? I didn't choose which one it is. There's a hole in the middle, so I'm using a washer. So we refer to this generally like this. It's the disc / washer method. We lump these together at the same time because it's the same method, just is there a hole in the middle or is there not a hole in the middle? Okay, so I'm using pi r squared h. I'm using the volume of a circular cylinder, the disc, or I might be subtracting out the middle part. So this method, there is another method we are going to learn next time that I'm going to take the same shape and there's a completely different method. Completely different. It's not even like this. That's what we're going to do next time. So I don't want to mention that one.
Oh, I just thought it was interesting that we got the same answer from this as the bowl.
That is interesting, isn't it?
Yeah.
Wonder why. Well, look at the big shape, the circular cylinder. It's exactly 81, and each one of these was half of it.
Yeah.
If I had gone higher than 9 or lower than 9, they would have been two different numbers. Chase noticed that we did a problem earlier with basically the same information, and we got the same volume for a different shape. But that was because we used the number 9. Had we used any other number, both answers would have been different. So remember I said it's possible to design a problem where they're the same, but it would only be the same once. I happened to figure out what that was accidentally. All right, let's try another one of these. find the volume of the resulting solid. Okay, now this one's weird. This one definitely needs a picture. All right, can everyone see that I got that thing right there. So y equal x squared, y equals 0, x equal plus or minus 3. Well, that's a really simple area. And of course, I'm rotating it about, wait a minute, I'm not rotating it about the x-axis or the y-axis. I'm rotating it about that. It's kind of a scary looking ring, right? It's a dangerous looking ring with lots of pointy things on it. But it's still a torus, isn't it? There's still a hole in the middle. Now, as a rule, we can only rotate things about a horizontal or a vertical axis. If we chose an axis that was diagonal, this would be way too complicated. I mean, it would require way more math than we're ever going to see. So I didn't rotate it about the x-axis, which would have been easier. I rotated it about here. But this isn't much different than if I just said, raise this thing up 2 units and then rotate it about the x-axis. It would be the same looking picture, wouldn't it? I'd still have that gap in the middle. So what we have to do is figure out, after I slice it, the radii here. So, which way do the circles go? Well, it goes like this. So is my slice vertical or horizontal? It's vertical. So again, I was like drawing the picture with the hole in the middle. So that's going to be my delta x. So that's y equal x squared. So that's definitely y. But isn't my radius this from here to here? So is my radius y?
Y plus 2.
It's y plus 2. Because there's an extra 2 units there. So the outer radius, I'll write here, is y plus 2. Now the inner radius is easy. What's the inner radius?
2.
It's
2.
exactly 2. Right? That's no variable on that one. That's a little bit easier. Okay? If you don't do this, there's a good chance I'll be using the wrong numbers. So I kind of need a picture. My picture doesn't have to be perfect, but I do need the right boundaries there. So because my line was 2 units below the x-axis, I essentially added 2 to create the radius. So now the volume of the eye slide is going to be pi times outer radius squared minus inner radius squared, as we saw earlier. And then it's delta xi. That's an awful delta x. Try that again. Now, I need to do a swap out. Should I square it, gather terms, and then swap out? Or should I swap out and then square it and gather terms? Does it make any difference? I have to square this at some point. So y does equal x squared. So what if we swap it out right now? Then that's xi plus 2 quantity, xi squared plus 2 quantity squared, is it not? Well, let's square that. I'm just squaring a binomial, so that would be x to the 4th plus 4x squared plus 4 minus 4. Oh, that's not that bad. 4's cancel. So that means this is pi times xi to the 4th plus 4xi squared delta xi. Oh, I think I can handle that one. what is the range of values on x? And you always want to put that in there because that goes into your integration.
-3 to 3.
Yeah, that comes from this here. Those are my vertical bars there. So -3 to 3, I know you sense it, don't you?
Symmetrical.
You sense symmetry. The reason you see a lot of symmetry is because we square a lot of things. And square things tend to be even functions to begin with. So I think it's safe to say the volume is pi times x to the 4th plus 4x squared dx from -3 to 3. I have symmetric limits. I have an even function. I definitely want to double it. All right, let's integrate this. So 2 pi times
1/5 x to the 5th plus 4/3 x to the 3rd.
and that's going from 0 to 3. All right, use the fraction key on your calculator. I'll do my part. There, that's my part. I'll even do this.
$846, I think. 846, I think.
846.
And 46.
Does anybody, any confirmation here? I think you're right. Anybody else get it?
Yes.
846?
Mm-hmm.
Was this hard? No, it was definitely tricky. I am allowed to rotate about any vertical or horizontal axis, but never going to be a diagonal axis. So the way you did it around the x-axis or the y-axis, this really isn't different. Right? It really is kind of the same thing. But I have to be mindful. That's why I think a picture is so important in this regard. Because if I don't draw a picture, doing this. All right, let's try another one along these lines. Maybe turn that. All right. Find the volume of the resulting solid. The only problem that you really don't love of these types of rotational problems are things involving trig functions in general, because you know you're going to be squaring things. And unless it's like a secant squared, there's a chance you might not be able to do the integration quickly and conveniently. So we typically stick with polynomial type things, not because that's the only thing you can do, but because we want to understand the big picture and be able to navigate through. As you go on further in mathematics, you're going to get the ugly.
Okay, let's try it
All
one more
right.
time.
Okay, so think good thoughts and project really, really positive thoughts. I really like to get through this. Okay, so first thing we're going to do, draw the picture in the XY plane. There's an order of things. Have to have the picture before I can rotate the picture. All right, so y equal x squared, x equal y squared. We just did this problem the other day, if you remember. Where did they intersect? Remember? We did this last day. We found the area of this thing. Where's that point? 1, 1. Yeah. Now I'm going to rotate this about the x-axis. That's how I always indicate which axis I'm going. So what is this? It's kind of a cool bowl. I'm looking at a bowl with puffed out inside. The inside's got like a lumbar support, you know, like you see this stuck out, that kind of thing. I don't know what the answer is. I'm not even going to guess what the answer is, but I'm going to set it up correctly. Now, because I'm rotating it about the x-axis, the most important part at this point is determining which way I'm going to slice it, because sometimes that can seem a little confusing. And what's worse is, we've got this today, we know which way to slice it. The next class, we're actually going to slice it in the other direction. Whatever way we did today, every problem we do today, we're going to do in the other direction next day, because it's a different thing we're looking for. Yikes. So I got to get this one first. It's going this way, so it's vertical or horizontal?
Vertical.
Vertical. So those will be my washers. Okay? In fact, I'll leave this one up here because it is so good, right? So that's still a delta x. What is my outer radius? Well, my outer radius is this curve here. But technically, this is y equals x squared. This was x equal y squared. That's not really helpful, is it? What do I need it to be?
All in terms of one.
So
All in
we're
terms
gonna-
of what? Yeah, which one? Y equals or x equals? X equals because I'm doing delta x cuts, so I need to rewrite this one how?
Just root x.
As root x, yeah. That's not that complicated, but I need to write it like that. Okay? So my inner radius is exactly the square root function. Okay, so that's root xi. I'm sorry, that was my outer radius, my bad. My outer radius is the root function. What's my inner radius?
Square.
The x squared. Now it seems odd at first, you go, wait a minute, x squared is the smaller of the two? Between 0 and 1, x squared is smaller than square root. Remember, between 0 and 1, raising things to powers makes them smaller. So yeah, that does make sense. Alrighty, so it's time for some blue here. So what is the volume of the ith slice? Now, hopefully you're seeing a trend here. Last day we found area problems, and what we did was we found an arbitrary rectangle, and if I could describe my area with one rectangle where the boundaries did not change, then it made it really easy to write the integral. But we did a couple of problems where we needed two integrations. We haven't had that problem yet, have we? And probably not in this context, we won't. So when I describe the arbitrary slice, the next thing is to say the volume is loosely estimated by the sum of those slices. It is equal to the limit, and then we write the integral. We're just skipping all the in-between steps because we realize the integral is going to look exactly like my arbitrary slice. So I've got to get this part perfect. So outer radius squared, I'll write it out formally, minus inner radius squared times pi delta xi. And what is the x ranging from in this case?
Zero to 1.
0 to 1? All right, so let's make this prettier. So pi times just xi Do you think this is going to present a simple or a difficult integration?
Simple.
Probably simple. And you have noticed that every single answer has a pi in it. Why does every answer have a pi in it? Automatically. Because my cross sections are all circular, so it's automatic. I'm never going to get a rational answer. I can't. No matter what your circle looks like, you always have a pi r squared kind of thing. So I just leave pi in the answer. So now my volume is. Don't say these are equal. That's one slice. This is the entire thing. 0 to 1 pi x minus x to the fourth. Am I looking for any form of symmetry in this one?
No.
No, my limits of integration are not symmetric. My function's neither odd nor even. Symmetry happens, you want to recognize it, you want to jump on it, it makes life simpler. And you've seen many examples today where symmetry applied. It doesn't apply to every problem. It can't apply to every problem, but it does apply often. Therefore, if you can take advantage of it, you want to. So the antiderivative is pi times 1/2 x squared minus 1/5 x to the 4th. I love this one. It's 0 to 1, so my answer is just a half minus a fifth, which is
3/10.
3/10. So 3/10 pi. You need to get to the point where this becomes the setup. The setup becomes automatic. The integrations are trivial. I am notorious for doing things like this on a calculus test. I gave you all this and I'll say, set up the integral to find the volume of the resulting solid. So therefore, what's the answer to the question? That. I set up a lot of questions where that's the answer. Why would I ask you a question where that's the answer? Because most of the next exam, you're going to be integrating. You're going to be doing stuff that involves substitution. You're going to be doing things that are not trivial, that may have some complication. Is there any way that integral is going to be difficult? No. So a lot of times on these applications, I'll just ask you to set up the integral. I won't even ask you to finish it, because why? You already demonstrated throughout a test your ability to integrate on harder problems. So I want to see that, and I'm going to say, if you could do that, I know you could finish it. Let's move on to the next problem. We do a lot of that.
Shouldn't it be x to the fifth?
Did I miss what? Oh, hold on. Yeah, thank you. Thank you, Alon. You're right. I got the fifth part right, but not the exponent. Good save. Fortunately, the one saved me, didn't it? All right. Everybody cool with this? We have two more things to go. The next thing, we're going to do two major concepts that are completely different, but both involve volumes of things. One of them's a rotation, one of them's not. And then the last lecture, which is the headiest lecture of the entire semester, we do two topics. We do arc length and we do surface area, which are the most complicated derivations in the entire course. And in fact, they're so complicated, I have edited many calculus books. I've reviewed many calculus books. I have over 20 in my office. My name's in a lot of them. I have never seen anybody get either one of these right. No, authors will give you the formula. They'll give you the final formula. And they'll say things like, you know this from geometry, like as if you knew this from geometry. I have never had a textbook where they actually explain the process. They just give you the formulas, because I don't believe the authors actually know how to do the process. They know it's correct. It's hundreds of years old. But they had no idea how to do it. And that's not a good way to do math. And from this point on, I'm just going to tell you formulas and you guys just memorize them, okay? That's not going to work, is it? You need to know why it's true, where it came from. Why? Because you're going to do this stuff in 3 dimensions. And you're going to derive a lot of this stuff, and you're going to tweak it. If you don't know how it's arrived at, then the higher level stuff's not going to make a lot of sense. So we do a lot of derivations. The next class, the derivations are very low level. The one after that, a bit more. So the week we come back, we finish the entire course content. Just to remind you, we don't have a test the week we come back. It's the following week. So it gives you a tremendous amount of time. That's why I say it is wise to do some reviewing over the break. Not just for the next test, but literally for the final exam. Because when we come back, it'll be a whirlwind. We have the last 2 lectures, an exam, and then all of a sudden it's reviewing for the final. It's never a great idea, let's put it this way, to wait till the very end of the course to start thinking about preparing for the final. Because if you have other classes, some of you have other classes, some of you have jobs. I've heard rumors that some of you actually have lives outside of here. And all of a sudden, you don't have 65 hours a day to do everything you need to do, and you're going to say, oh shoot, I don't have enough time. And every semester I hear the same thing. People say, I wish I had started sooner, because they realize just how much is in front of them. So I say, start soon. Don't spend your whole break reviewing, but do spend some time on your break reviewing, so therefore when you get back, it's not stressful. You're not putting out fires, because there's not a lot left. And today was the 21st quiz. So if you're taking the final exam, you now get to officially say, I can start dropping my lowest scores because I've turned in more than 20 quizzes. If you've turned in more than 20 quizzes. Okay, go ahead and stop that. I'm going to give you guys a little bit of